Okay, thank you everybody for attending. And thanks Kathy for the introduction. I'm Daniel Least, the Group Leader for Advanced Manufacturing of Metals. I've been working in the additive manufacturing space for about 7 years. I used to be the Director of Lab 22. And I'm also a visiting research fellow at NASA looking at construction of 3D printing for spacecraft and also remote area printing as far as the space industry is concerned. I'd like to introduce my colleagues here. James, could you introduce yourself, please?
Good afternoon. My name is James Sanders from Formero in Melbourne. We are a bureau service who offer 3D printing across half a dozen different platforms, mainly specified around bound plastics. So some of the content here today might be a little bit different to what we do on a day-to-day basis, but we can certainly have some good input on that.
Next on the line, we've got Ben.
Yeah, hello everybody. It's Ben Hockley. I'm the head of sales for Speed 3D, who are a Victorian OEM of a cold spray metal deposition printer, and we're exporting our cold spray printers around the world, mainly for defence applications. But yeah, we're really keen to work with the mining industry as well.
Thanks, Ben. And next we've got Neil from Titomic.
Neil Matthews from Titomic. We're an organisation. We'll talk about the technology, which is a metal deposition technology, already been mentioned in cold spray. My journey started in about 2004 in the concept of the ability to use this technology for sustainment primarily, and now we're looking at it for a large-scale application. One thing I can tell you, and I mean my journey started in the aerospace industry, it does work. It's very, very effective, and I think as we deliver today, you'll see that this technology is a very, very valuable tool for all industries, in particular the mining industry. Thank you.
And last, not a manufacturer, but an end user, we've got Lee.
Hi everyone, Lee Djumas, currently working at Woodside Energy and leading the additive manufacturing program there. I'm not here representing them today, just to be clear. But hopefully can share a bit more on the customer experience of implementing additive manufacturing into operations in my experience in the energy and resources space.
Okay, thanks a lot. So I'd like to kick off with a question around the development of this technology. So most people are familiar with additive manufacturing, but when they think of it, it's the hobbyist, the thing you can pick up from Bunnings and print at home. That's not really what we're talking about here. So I guess to each of you in turn, I guess, how has additive manufacturing developed lately? Now it can be an industrial process, and how do your processes work in an industrial setting? So.
Yeah, I'll kick that one off. I think for me, who I've been around in additive manufacturing since the mid-90s, is that in the early days it was very much focused around what we call rapid prototyping. So it's about developing products, getting your products to market faster. Over the last sort of 10 years, though, in our business, is that the emphasis has been much more on manufacturing. So it's building and producing end-use products on these 3D printers. So it's not just about developing products; it's about using this technology to enhance everyday goods and products, whether it's for mining or for any other industry or for aerospace, and actually building end-use goods. And it's not just an experimental or a research game; it's actually used for production.
Yes, so Speed 3D's cold spray metal printers were developed with manufacturing in mind. Basically, our founders wanted to develop a faster way to make metal parts because they were involved in manufacturing themselves, and there was a lot of problems they were having with the casting process around the time frames, and if there was errors, there was a big delay in the next iterations. So they were keen to look at what technology could be used to make metal parts manufacturing much faster. And so cold spray had been used for a long time for coatings, as was mentioned earlier. So really what we've developed is the software algorithm that can control the deposition of the metal to create the 3D shapes. And then the further advancement of our technology is to actually make that printer deployable. So we've been having a lot of success with the defence, where they can actually take our metal printers near the battlefield front lines and actually print repair parts and repair broken parts and replacement parts at the point of need, which we imagine is very similar to the mining sector with a lot of the remote logistics around supply chain. So yeah, that's how our technology has evolved.
Okay, so very, very similar. I think our story started where Defence really had problems with operational availability. So we look at this technology in relationship to uptime and operations. That was a real problem. There was a cost element which is quite significant, but when we reduced downtime or operational unavailability and we returned it by 75% in a very short period of time, there was a lot of interest in the technology in as much that you could deliver it what we call at the target or very close to the target. You didn't require disassembly, but the most significant part about this technology, you can utilise it without altering the original design. So the original part, form, fit or function is retained, but you can basically rebuild the damage. And we're talking about simple things of damage which appear simple but very, very cost a lot of money: corrosion, erosion, impact, all those sorts of things. So this is a technology to add on, but I think as we've gained much, much more experience, it also has another area of opportunity in what we call large-scale thin-walled manufacture, which existing manufacturing processes will not be able to do.
I mean, not a great deal to add there, other than I would say that AM is just another tool in the tool belt, really, just another type of manufacturing that we can make use of. How we integrate it into our manufacturing process is kind of the secret sauce. So understanding the behaviour, the material properties, there's now a really strong track record of it in the field, and we understand what it can and can't do. And I think that's kind of the key to the technology. So kind of moving beyond the technical and into the implementation. So, yeah.
Yeah, thank you. So yeah, the world's changed in the last 3 to 4 years. We lived in a world where everything was built somewhere else, and we brought things to the point of use. How do you guys think that additive manufacturing can change that? What will be the effect on supply chains and logistics, and how can additive affect that, especially for the mining resources industry?
Yeah, sure. Obviously, the breakdown of the supply chains as a result of the pandemic, really exposed a lot of weaknesses and vulnerabilities. So yeah, it just put more attention on to the advantages of additive manufacturing. Being able to to make your parts at the point of need or even closer to where you are. So, and that's once again defence. Our most critical infrastructure saw the vulnerability there, and so they're moving rapidly. I think faster than some other industries to actually using the technology. So yeah, I think that's really just created extra additional focus on additive as being a solution to what is one of the biggest problems we had to face.
Yeah, I think the other thing too is that we haven't been stagnant in the additive manufacturing. It's evolving quite significantly, and more R&D we're doing is, we now can make multi-layer builds, so we can tailor build structure to meet all sorts of requirements like thermal protection or thermal enhancement, radiation protection, impact resistance. So the technology, as you delve into it, it is a layer by layer build process, but you can change all those parameters. We're now even in a world where we can make new materials that you can't make conventionally. So all of a sudden we're being not only challenged with people's requirements, but this is a technology that can quite often respond to those difficult questions. Can you do this? What about that? So it's that level of emergence that we've got that's feeding off customers' requirements. So it's quite flexible, and it's maturing all the time. I think some of the examples would be coatings, formal coating processes can now be replaced by these sorts of processes. The requirement to, in terms of one of the other things, is a green consideration where lots of metals are recycled, and there is a green cost to that. That can be avoided. So you start looking at a much broader range. So I think what we're talking about is a technology that's emerging and can solve a lot of problems. Won't solve them all, but certainly can help significantly.
Yeah, I think moving on from that, I think what we're starting to see over the last few years is that companies moving forward through their traditional manufacturing cycles, and they're actually embedding 3D printing in their production systems right from the start. And we're seeing awesome Australian companies now building lightweight drones that are almost 90% 3D printed right across the product, and they're using these UAVs to deliver medical goods to remote areas and dropping logistically packages and things to remote locations. So getting back to your supply chain, that becomes important because we've got these companies doing these awesome, amazing things like using 3D printing to accelerate and produce products that they couldn't do any other way.
I think from a supply chain perspective, certainly since COVID, when you've got the cost of goods, tripling, lead times doubling, if not more, especially for large companies, building a resilient supply chain is quite difficult. And I think with AM, the agility and the nimbleness of the technology allows for it to produce many different kinds of things very quickly. And so having that as a contingency or at least enhancing capability certainly helps with the resiliency in supply chain. So certainly post-COVID, it's been embraced much more quickly, I would say.
Yeah, and I guess one question that we always get around this, it's like, yes, you can make this, you can make that. If you're a design engineer or a maintenance engineer that works in these companies, it's like, how can I be sure? So what I'm getting at, I guess, is the standards and the capabilities. People are comfortable with the standards in the casting industry. How are we going around developing standards and acceptance for additive, again, in this industry, in the mining resources industry? I think Lee's got something.
Do you want me to start? Yeah, it's been a huge focus for me, at least in the last couple of years. The industry bodies are catching up, is the short version. So institutes like ASTM, DNV, ASME, the list goes on, NASA, SAE, have been building some pretty robust standards to support. And really with that's when the adoptions come along. So it's very heartening. It's not a fast process, but I think from the mining perspective, if you've got industries like aerospace, like oil and gas, biomedical, you can be fairly confident that these standards are going to cover many of the applications that you're going to see in mining. From a QA/QC perspective, they're very robust, and they're not necessarily easy to meet, but a lot of these companies can do it now. So I think you can take away a lot of confidence in the fact that these standards are there and they're being implemented quite widely now.
Yeah, I think that's a very important question, and it's interesting that organisations like SAE are reaching out, for example, to Titomic to write cold spray specifications and things like that. It's missing, but I think one's got to realise that behind the specification there's a whole stack of fundamental standards, design standards, mechanical property standards. These are all being done. It's how they're packaged up. And we're very, very confident as an industry, I think, right across the board in Australia, that we can provide any body of evidence that's required to support change. Now, whether that's under the SAE or any other specification, we'll get there. But I think that work has been done. It's been done through the likes of CSIRO, all our academic institutions. So there's an enormous amount of effort going into the development of body of science to overcome that valley of death, and it does exist. So it's not limited. It's quite expansive, and it's available.
Yeah, I totally agree. The standards are really important, and obviously it's a younger industry than some of the legacy processes for manufacturing. But so there's a lot of hurdles to work through the different standards, and I guess the use cases for whether that research is being done or not is on a needs basis. So, for instance, we're currently working on a funded project with the US Navy to develop a particular material that they need certified for their submarine program. But putting aside the mandated requirements in certain applications for certifications, there's also a lot of low-hanging fruit around additive manufacturing for applications that perhaps don't need certification, or even if they do need certification, the need is just too critical. So as an example, In some settings, they'll use like a traffic light system. So a red part is a part that you must be certified, no questions asked, just walk away if you don't have the certification. But an amber part or a green part, go and print it. But an amber part might be something that does need certification. But in this particular instance, we can justify why we would make that part now. And we can either wait for the original REM part to come further down the track, or just the need is so great, it's either going to save lives or millions of dollars. So we will go ahead and print that part now. So we call that the amber part. So yeah, that's sort of alongside the certification question is there is low hanging fruit around. Not all applications need certification.
I was going to ask if that typo in the title's intentional. The additive manufacturing.
Oh yes.
Who did that?
Once you get into it, you just can't get out of it.
Yeah,
That's the way
that's
it goes. James, do you have anything to add to that one? Or?
No.
You don't have to answer all one. I mean, I'd like to touch on that amber type part. So are we talking around, obviously you're not talking life critical parts, that would be pressure vessels, that type of thing. So, I mean, I've heard them talked about, say, limp home parts. So if you've got a truck in the mining industry, I've never really worked in mining, so I don't know if this happens, that's stuck on a road and things can't get past it. You can take your limp home part and that'll get your truck from blocking that road to the workshop. Or, I mean, so it may not have to last. I mean, a normal part, if you're buying it from an OEM, you're talking 5-year lifetime. This has got to last 3 months until the original part comes. Is that what you mean by an orange part? I mean, or do you have some examples of orange parts instead of me just thinking off the top of my head?
Yeah, that would be definitely one. I mean, another one in the keeping with the mining industry. If you've got something flooding, and you can't get the replacement part for you've been told it's a couple of months away, then maybe you would make a pressurized part with the additive manufacturing process if it's going to solve a multi-million-dollar problem or potentially put lives at risk.
That part or that repair can last the lifetime. And what we're effectively saying is that from a risk point of view, if you can get by, if there's another pathway for a redundancy or those sorts of elements where we don't have to demonstrate endurance and durability necessarily, you can basically implement these. So again, we're not treading in that area where we're conscious. See, I think that's a good point. We're conscious of design criteria and the specifications and standards. And I don't think there's any of us up here that would say, go and put this critical part, which is probably one that you'd have catastrophic failure, put it on and we'll worry about the testing later or something like that. None of us are that inclined, but we can give assessments of repairs, of new parts, of longevity and those sorts of things, but in a benign environment, i.e. that if it fails, you're not going to cause a catastrophic event.
I think it's just the point around business cases is so important. There's many different ways you can cut up a business case for AM, and we've touched on some of them already. Some might be these temporary, but the way in which you can develop the business cases for AM are quite diverse, and we can put them in critical applications. We can put them in pressure retaining service for hydrocarbons, for example, and we can fly in them, right? I mean, gas turbines from GE, Siemens, all the big companies now all have metal AM parts, right? Where generally regarded as some of the most critical bits of equipment are 3D printed. You can't buy them without them. So amber is good, green is better.
I mean, and the traffic lights don't stay the same colour the whole time. Things will start off in amber, and then as we get more evidence, more development of the technology, we can move them into green parts. Amber parts is sort of not where we want to live. That's just a transitional place to be. Yeah. And generally you move pretty quickly through amber. I mean, if the traffic light system is going to work. We sort of look at, we've touched on here, repair, digitisation. So I guess the next thing that I'm sort of interested in is using additive for automated repair. But sometimes the drawings aren't right, or sometimes over the years somebody's put a few extra holes in or added something to the part. So how does sort of additive handle the variability that can occur in repairs? It's not the same repair every single time.
Okay. First of all, additive manufacturing produces, in the main, near shape for metals, right? So you can get a very, very close proximity. There is always an element of post rework, post machining, post heat treating. So whilst we're in metals, heat treating will always be there, although we're trying to think of some smarter ways to do it. But so there's always some there. So at the moment, what you tend to do is you'll overcompensate. If you don't have the direct profile, you'll overcompensate. For relatively simple platforms, flat plates, bars and things like that, you can get fairly accurate deposition. It's when you get complex parts that you really need to look at the digitisation. And not only that, is that a lot of the depositions are robotically deposited. So you need to identify the tool path, because there are elements within the deposition that are critical, and that's nozzle angle, standoff, overlap, all those sorts of things which have got to be programmed. So most of the robotics are programmable, and they rely heavily on knowing what the surface shape is and things like that. As I say, I think what we'll do as we go along, there's a couple of things that's going to happen, is that the introduction of surface scanning, I think, will be a must, and that will translate into a tool path for the deposition as we go along. And also we'll see process development in what we call in-process monitoring and control, so that we can actually monitor what's happening on the surface and during the build, and compensate during the process to deliver the optimum outcome. So all of that's going to happen. Machine learning is going into this as well. So what we're, again, I think as an industry, is basically recognising the need to look at all these other elements of AI and digitisation and those sorts of things. So again, it's not a separate entity in terms of manufacture. We're going to use most of the tools that are available and somehow incorporate it in the solution.
Yeah, I think what you were describing is customization, which additive manufacturing is one of its biggest strengths, is the ability to rapidly customize and improve design. So yeah, I think it's one of the strengths of additive, actually, being able to rapidly make design changes. Yeah.
And I think, coming back to the digitisation, I think other industries have done a very good job in engaging with that side of the prototyping or additive manufacturing, where they've built processes around capturing the shapes before they do anything. For instance, in orthotics, where that's a very big part of what they're doing, is they're scanning, they're bringing that into a model, and then 3D printing it as a part of the process. So I think in terms of digitisation, I think I mentioned to you earlier on, I didn't see many signs around here of people that are engaging with reverse engineering and picking up the existing 3D model, which would be important for the mining industry, is to get that in situ beforehand.
Okay. I guess another thing, we're talking about putting these things on site, or putting these things in situ, or again, not overseas. We need people to run them. How do you think our supply chain of people is coming along, and what type of engineers, designers, apprentices, who can run these machines, and where should we get them from? Or
slowly. It's actually been running a business for as long as we have, and trying to get a workforce coming through that are experienced in running 3D printing equipment. We're finding that on that apprentice side of thing, where we'd like to engage and get people skilled across different types of 3D printing technologies, it is a struggle for us to find, and we've recently been engaging with industry bodies to try and get that off the ground. But it has been slow for us in trying to engage. We're seeing quite a lot at the university levels, but for us as an operator, it's a little bit high. So the apprentice model is something that we're looking at the moment, but it's slow going.
Over the last few years, particularly just recently, there's been a lot of extra focus around TAFE, which has been really encouraging. They're incorporating additive technologies into their curriculum. So I think there's efforts being made to backfill that pipeline in the future. The other thing that's relevant to that question is around you're saying who's going to operate it. So automation of the technology makes it more accessible. So a lot of these devices, you don't need a PhD, you don't need as many skills as perhaps what you once did. So, and that's because the level of automation within the technology is improving and increasing. So yeah, a couple of points on that.
Yeah, I think it's a very broad question because the technology comes in so many formats. It becomes in big machines with lots of robots and lots of powder feeders to the low end of it, which is a handheld device. And from that point of view, the handheld device is very similar to a welder, and that's the sort of experience level because most of the input variables are defined and the powder's defined, and so it's a range of skill sets. The closer you get to the target, and if you go into the manual process, believe it or not, the simpler it is to apply. The more complex you get and the more challenging materials you get and all those sorts of things, there's a level of skill set and understanding that comes with all of those. So it's, it's varied is the answer.
There's a skills shortage across the board, right? And it's not immune from it. So, yeah.
Yeah, I mean, I think just from a personal point of view at CSIRO, we have, I mean, Kathy showed up before, 10 different types of machines. Most of those machines are run by ex-tradesmen so if you can run a CNC mill, you can run an additive manufacturing machine. It's around dealing with digital files, tool paths, same sorts of questions that they get asked. So, I mean, that's who we have running our machines, and we have everything from the state of the art to more manual type kit, and we can get a good tradesman can run that type of machine. So I've got kids in high school and they're using additive manufacturing in their schoolwork, so hopefully the understanding will at least come through a little bit quicker.
Minecraft's been a big help too.
Yeah.
I mean, yeah, robots are always great, and yeah, they work 24 hours. They don't take sick days. They don't come in bit seedy on certain days, so that's good. The environmental impacts is now something that we always have to pick up, and the full life cycle of everything. So, I mean, how does additive manufacturing kick into those types of concerns? It's always something that we're looking towards.
Well, just in its innate, the way it's been designed from the start. I mean, as Kathy mentioned earlier on, that being an additive process where we're not removing large chunks of materials inherently, it is environmentally friendly, I guess is a word to use. We see some technologies are better than others at being environmentally friendly, especially when it comes to raw materials. We have some processes in-house that might use up to 95% of the raw material through to completion and before it gets thrown out, where other technologies might only use 50%. So some are better than others, but some are doing really well, like HP have done a really good job with their technology, and the recyclability on their materials is actually very good compared to some of the other technologies.
Yeah, we're lucky actually. Just a month ago, Swinburne published the results of a study that they had done into cold spray and its environmental carbon footprint, energy usage, and yeah, it was significantly less than the legacy processes for metal manufacturing using cold spray. So I think it's minimum 30% less energy required.
I think not only is it environmentally friendly, that's a technology, but I think the benefit, a huge benefit, is to replace what we call legacy processes, such as all the electroplating's done, the chrome, the cadmiums, and all this thing, all those sorts of things, which we know are very, very hazardous to not only our health but certainly the future. And you now have a technology that can basically replace those, and I think that's a significant benefit. And the other one I mentioned briefly before is that we talk a lot about recycling. And yes, it's easy to throw something that's damaged away, and somebody, particularly metal, they'll recycle it, but there's an awful lot of energy being burnt in that recycling process. So again, if we can avoid things being recycled as an industry, that's another big plus for the environment. So there are lots of other elements just outside the technology that has green benefit.
Well, there's three main ways it helps. Two of them have been mentioned. The last one's shortening the supply chain. So If you can manufacture closer to the point of need, that's always beneficial. And hopefully unlocking new repair and refurbishment options as well is critical.
So I know that additive manufacturing, I believe, is coming and will transfer into industries of all types. I guess if we pulled out our magic wands now and there was one hurdle that you guys are continually running up against that you could make just disappear overnight, I mean, what do you think that hurdle would be? And I guess if you can, how do you have a plan to get rid of it? Or what help do you need to get rid of it?
I think you all get quiet. It's developing business cases. I know I'm repeating myself there, but being smart in the way that you implement, so it requires a good knowledge of the technology. It requires a good knowledge of the applications, and how you bridge those two gaps takes some creativity. I mean, they're not necessarily straightforward, but the stronger the business case, the hurdles will be overcome. If it makes sense, if the dollars make sense, we'll figure it out. So I think a lot of the effort and energy should be put into working on the business cases. So whether that's working with OEMs, the end customers and the manufacturers and everything in between there, this is the primary hurdle. I think all the others, I think, can be overcome. The rest are technical, and the technical knowledge is there. We can figure all the other things out. So my answer is developing business cases.
If I had one choice, it would be to say that those thousands of years of empirical data that's been generated through metal development and things like that, I wish that probably could disappear and not be the standard, because I think we've got to open our eyes up about the technology, the concept of layered manufacturing. It's been around for a little while. I mean, we're all very comfortable with composite layups and some of the polymers, and so I think we just got to come on board with the concept that you can build metals through a layered process.
Oh, magic wand, I'd probably just say that maybe the word additive manufacturing is so broad that people perhaps come to it with preconceived ideas about what it means, when it's actually really multifaceted. There's, we've talked about a range of different technologies here. So yeah, maybe that's the only thing I'd say is, sort of look at things specifically as and how they relate to the application that you're trying to solve.
Yeah, I think moving on from that answer there is that it's people's expectations on what additive manufacturing or 3D printing or whatever you want to call it can deliver to a customer. Is that it isn't a magic wand in itself. It is an industrial process, and there are variabilities throughout all the different types of technologies. So some people come with a good broad mindset of how it can be used in their business or in their use case. Others come to the table with, why can't you do this? So knowledgeability and education to people would be great overnight.
What do you mean, Ben? It's not called additive manufacturing. It's called addictive
manufacturing.
Come on.
I mean, I think for that, if I had mine, I mean, from Lee's point with the business cases, I'd like people to look at their business cases and not just look at the cost of the part manufacture, but look at the life cycle cost. And I'm sure some companies do that, but again, some companies that I come involved with, they sort of look at but this part costs more than that part, therefore it can never be more efficient. And to Neil's point, we're comfortable with defects in castings. My background is castings before additive manufacturing. Castings are used everywhere. Castings are full of holes in the correct positions and the correct sizes. But if they ever see a little defect in an additive manufactured product, it's no good. So it's understanding that it's not just about being perfect, but it's about being perfect in the correct areas or being good enough. Standards are there, and there are a lot of different standards. Pick the standard that's right for you. It doesn't have to be perfect. I guess we're nearly out of time. I've got sort of a few minutes to go. I mean, I guess I'd call for a closing statement, I guess, from a lot of you. I mean, what would you like people to take away from this? What would you like people to think about and how they approach additive manufacturing and how it can work for their business? And again, we'll start from this end. James?
Okay. Look, I think, for me, I'd like to see people looking at additive manufacturing at earlier stages in their product design life and design cycles. I think the more people can adopt additive manufacturing earlier, the better off their products will be in the long term.
Look, I guess this opportunity to speak to the mining industry, I can't miss the opportunity to talk about, where our company in particular, we're solving problems in the battle space, and we see a lot of the similar challenges in the resource sector about, rugged remote sites and the supply chain of getting parts to difficult places. So I guess, put a call out there for, interested parties to want to look at trials and evaluations to see if we can quantify what the benefit of additive manufacturing is in remote locations in the resource sector.
Yeah, I just think we are a world leader in this technology, I believe. We have an unbelievable success story and collaboration between the academia, the research, the customer and those sorts of things. So I just would like you to reach out, because it's here. There is a knowledge base here. There's a lot of science behind it. Don't be fearful of that. And I think they got the name right, because from my point of view, additive manufacturing is an addictive technology. So I think they've got it spot on.
I guess the message is other sectors are using it widely, and I think mining's missing out, and there's some low-hanging fruit there to adopt. So I'd encourage anyone to take a look at it, look to other sectors in the country, and see what lessons you can learn.
Thanks, gentlemen. I guess I'll put my own in, even though I'm not, again, I think, but sort of almost touching on what Ben said, that calling this broad variety of techniques that we have at our disposal additive manufacturing can actually be limiting. So if you know what you want to do, reach out to companies, to academics like myself and other universities and say, this is my problem. Do you think additive can help me? And there may be a technique that can help your problem. We've moved past the point of being evangelists saying that additive will solve all your problems. And from a personal point of view, and I don't want to speak for these guys, but I'm hoping it's the same, that if additive actually won't solve your problem, we're not going to push you down that path, because, get a good experience, you tell 2 or 3 people, get a bad experience, you'll tell everybody you come across at one of these meetings. So we're not here to try and push a technique on you. We really are here to try and help you solve your problems. So again, reach out to companies, reach out to people, reach out to each other and figure out, how have you done it, or how can you do it. That's what I'd like to leave you with. So we're just about out of time. So, thanks for coming, and thank you for joining us. And thank you very much.
Thanks for having us.
Thank you.
Thanks.